This is the tutorial for the analysis of well log resolution from SeisRP. Once the data has been loaded, we can run any of the modules under the analysis column. We're going to start by doing the analysis at well log resolution. This module creates log plots and scatter plots for different types of properties. The property type is selected with this drop-down menu. It can be absolute properties, relative properties, reflectivities, or the results of the petrophysical evaluation, in this case porosity, lithology, fluids targets, and finally depth. The attributes that can be plotted are selected with this drop-down menu. For the absolute properties, we can evaluate P-wave velocity, S-wave velocity, density, brittleness index, a series of moduli and moduli times density, and then finally elastic impedance for the near angle, elastic impedance for the far angle, and gradient impedance. Similarly, for the relative properties, we can evaluate P-wave velocity, S-wave velocity, density, the relative values of different moduli and moduli times density, and relative elastic impedances and relative gradient impedance. We can obtain the reflectivities of the same properties, and here we can also obtain AVO attributes, in this case normal incidence, gradient, curvature from Shoes, and then amplitudes for the stack from the near angle to the far angle, as well as near angle stacks and far angle stacks. Let's start by evaluating absolute properties. And let's display BP, Vs versus density, create the scatter plot. That is the scatter plot. For some of the properties, we can also overplot empirical relationships. So let's do the scatter plot. And here we have P-wave velocity, S-wave velocity, color coded by density, and at the bottom we have overplotted Castaña's mud rock line. Let's now look at the log plot. The log plot is going to have 4 tracks. The first 3 tracks correspond to the attributes selected, and the 4th track is the results of the petrophysical evaluation. This well had a binary petrophysical evaluation, but we could have as well plotted a multi-mineral petrophysical evaluation. Here these points in black correspond to the target or to the pay flag. Before proceeding, let's plot a smaller range. Instead of going from 3000 to 3300, let's evaluate from 3100 to 3300. So the log plot. Now the log plot goes from 3100 to 3300. And the scatter plot, which goes as well from 3100 to 3300. Let's repeat it without the empirical relationship. Once we have these 2 plots, we can do some analysis. We can select a point in the scatter plot with mouse button 1, and this is going to create a line at the corresponding depth, or we can select another point with mouse button 3, and that's going to create a red point in the scatter plot and the corresponding red line at the depth associated to that point. Mouse button 2 deletes the points and the lines. We can do something similar in the log plot. We do mouse button 1, and it's going to create a blue line and the corresponding point in the scatter plot. Mouse button 3 creates a red line in the log plot and the corresponding point in the scatter plot. Mouse button 2 deletes lines and points. Let's now look at reflectivities. Let's do normal incidence times gradient, and let's color code by target. This is the log plot and the scatter plot. In this case, the target is not very useful in track 3, partially because we already have the target annotated here in the petrophysical evaluation track. So let's repeat the log plot, but now let's select porosity. So now we have in track 1 normal incidence at well log resolution, track 2 gradient at well log resolution, and in track 3 we have the porosity. We can still do what we did before. Let's say that we want to identify the point where this porosity changes. So we do mouse button 1 and we identify that point, and let's see now the point where porosity is reduced with mouse button 3 creates a red line, and it shows the red line in the scatter plot. Let's take a look at some relative properties. Let's do relative k rho versus relative mu rho, and let's color code by brittleness index. The scatter plot and the log plot. Let's say that now I want to have the same scale for the x and y. So here I'm going to go in x minus 1.5 to 1.5 and in y minus 1.5 and 1.5 and recreate the scatter plot. So now the scatter plot is goes from minus 1.5 to 1.5 in both x and y. And I'm gonna redo the log plot as well. And in this case now we have the x-axis for both the scatter plot and the log plot going from minus 1.5 to 1.5 for the x and y axis. I'd like to use this cross plot to illustrate some of the properties under the general box. I'm going to start with the chi-angle. The chi-angle is the rotation angle that the data is going to have in reference to the coordinate axis. So if I do here a minus 45 degrees chi-angle rotation and do the scatter plot, sorry, minus 45 degrees, and do the scatter plot, we see that now most of the energy is aligned in the x-axis. If I look at the log plot, I can see here that most of the energy is aligned in the x-axis as well. Just for thoroughness, I'm gonna repeat this with 0 and do the log plot for completeness. So here it's the properties without being rotated. We have energy in the x and the y axis, and here after rotating by minus 45 degrees we see that most of the energy is in the x axis. To illustrate the effect of the D-trend filter length, I'm going to plot here absolute p-wave velocity, relative p-wave velocity, and just to change this, let's color code by sand volume, and I do the log plot. Okay, before doing the log plot, I need to reset the coordinates. Okay, so I have a P wave velocity, S wave velocity, and sand volume. Here we can see a red line. This corresponds to the trend and represents the low frequency in the data. If I modify the filter length from 300 to 15 meters, sorry, this should have been the log plot. I see that the red line is not as smooth anymore, and the relative P wave velocity does not deviate as much when we have a short filter length than when we have a long filter length. So the length of the filter should be selected based on the bandwidth of the seismic data. To illustrate the display units, changing the display units, I'm going to leave here BP. I'm going to selecting here the absolute BS, and here I'm going to select the depth. I'm going to return this to 300 and do the log plot. So we have here the log plot, P wave velocity, S wave velocity in kilometers per second, depth in meters, and depth in meters. If I change the units to English, you can see that the units changing here as well as the values. This is in meters, this is in feet. If I plot this, the log plot, now the plot units are in kilofeet per second for the velocities and depth in kilofeet. The same is true for the scatter plot. The scatter plot now has P wave velocities in kilofeet per second, S wave velocities as well in kilofeet per second, depth in kilofeet, and if I go to metric, they are going to be in kilometers per second and meters. The last parameters that we are going to evaluate are the near and far angles, and these take effect when we select things like the near elastic impedance and the far elastic impedance. Let's color code this by let's do it by water saturation, and let's do the scatter plot. To do proper evaluation with the next display, let's fix the axis. X, we want it to go from 5 to 14, and Y from 2 to 14. And change this to be 0 and 35. Let's do the scatter plot, and that would be the result of comparing the elastic impedance from 0 to 35 degrees and from 10 to 45 degrees. This concludes the tutorial. We're going to come back to this after doing the fluid properties computation, and then we're going to do similar analysis doing fluid substitution. Thank you.